Why did Billings, Montana just hit 111 degrees, a mark meteorologists initially called an all-time record for the city? And why did that same kind of extreme heat hit the east first, then completely flip to the west 2 weeks later? That's not two random heat waves. That's one atmospheric pattern doing something specific, and it starts with the jet stream. Let's define that term first. In plain language, the jet stream is a fast-moving river of air high above the surface that essentially steers our weather systems. When it flows in a relatively straight, tight line, weather tends to move through quickly. Storms come, storms go, and no single pattern sits in one place for long. This summer, that's not what happened. Instead, the jet stream buckled into a wavy, stretched-out shape, and in a very real sense, split its energy between two separate zones. On its own, a wavy jet stream pattern isn't unusual. It happens plenty of summers without producing anything historic. What made this pattern worth investigating is what it did next. It didn't just wobble and pass through. It locked into place, first parking a heat dome over the east, then swinging that same blocking pattern over to the west. Let's walk through how scientists actually investigate a pattern like this, step by step, the way meteorologists did in real time this summer. The first thing they look for is a blocking high, a large area of high pressure that essentially refuses to move. In late June, that block set up over the central and eastern United States. Meteorologists described it as a lid on the atmosphere, compressing and heating the air underneath while also suppressing rain and cloud cover. That lid effect explains why this heat wave felt so relentless. A blocking high doesn't just raise the daytime high, it also prevents overnight temperatures from dropping, since there's no rain-cooled air moving through to reset things. Step 2 in the investigation is tracking where that pressure system sits relative to the jet stream itself. Heat domes tend to form specifically where the jet stream turns northward, arcing up and over the high-pressure zone. That arc creates a feedback loop. Hot air gets pulled northward beneath the ridge, which further strengthens the high pressure sitting above it, which then locks the pattern in place even more firmly. By the 4th of July, that eastern block had grown enormous. More than 200 million Americans were under some form of heat alert, and by the time the wave finally broke, it had shattered more than 1,500 daily temperature records across 40 states. Washington, D.C. recorded its hottest 4th of July on record, reaching 103 degrees with a heat index between 110 and 115. Atlantic City hit 106 degrees that same day, and Philadelphia canceled its parade because of the heat. The same blocking pattern reached north into Canada as well, which tells you how large this ridge actually grew. Ontario and Quebec saw temperatures climb past 37 degrees Celsius, with a feels-like reading of 46 degrees Celsius recorded in Ottawa on Canada Day. That heat also triggered large thunderstorms in Canada on July 1st, leaving thousands of homes without power. Extreme heat and sudden severe storms often arrive together at the edge of a blocking pattern, where the boundary between hot, stable air and incoming moisture becomes sharp and volatile. That's step 3 in any real investigation, confirming the pattern with hard numbers, not just a general sense that it felt hot. A total of 148 individual temperature records fell across the eastern U.S. on July 4th alone. Now, here's where the investigation gets genuinely interesting, because the story doesn't end with the eastern heat dome. Around the holiday weekend, the jet stream did something forecasters had specifically flagged in advance. It shifted. The same ridge of high pressure that had been anchored over the east began sliding westward, essentially trading places with the cooler air that had briefly been sitting over parts of the west. That's the split. Not two unrelated heat waves happening to occur back-to-back, but a single wavy jet stream pattern handing the same blocking high off from one half of the country to the other. As the jet stream bulged northward over the west, a fresh area of high pressure began building there too. Forecasters expected temperatures to climb to somewhere between 10 and 20 degrees above the 30-year average by the middle of July. That's exactly what happened. Phoenix reached 113 degrees across July 6th through 8th. Salt Lake City set a new all-time high of 109 degrees on July 12th. Denver saw highs in the low to mid-90s initially, with forecasts calling for the upper 90s to near 100 degrees by the following weekend. That kind of steady, days-long climb is the signature of a blocking high settling in, rather than a brief, single-day spike. A temperature inversion also developed beneath this western heat dome, according to AccuWeather meteorologists tracking the pattern. That inversion trapped light winds near the surface, which allowed wildfire smoke to build up over a broad area and significantly degrade air quality across the interior west. Then came Billings, Montana, reaching what the National Weather Service and ABC News initially called an all-time heat record at 111 degrees on July 12th. That's the specific number that opened this whole breakdown. Here's an important piece of honest context, because a good investigation follows the data wherever it leads, even when that complicates the headline. Some climate researchers pointed out that Billings had actually reached 112 degrees back on July 31st, 1901, based on archived climatological records. That doesn't erase how extreme this July's heat was, but it's a useful reminder that even genuinely historic heat events deserve a second look before a record claim gets locked in as absolute fact. Let's zoom out now to the bigger pattern behind all of this, because a split jet stream doesn't happen in a vacuum. Climate researchers have been tracking an increase in exactly this kind of stuck, wavy jet stream behavior over recent decades. Researchers refer to these events as planetary resonance patterns, and they've shown an uptick in frequency as global temperatures have risen. That trend doesn't prove any single event was caused by it, but it does describe the broader environment these heat waves are forming inside of. There's also a specific ingredient present this year that deserves its own layer of the investigation. El Niño conditions were confirmed by the National Weather Service in mid-June, with some meteorologists specifically flagging the possibility of a super El Niño developing as the year progressed. El Niño tends to shift where the jet stream sits and how strongly it waves, which lines up directly with the pattern we've been tracking. Climate scientists have said this El Niño pattern raises both the odds and the intensity of heat waves during a year like this one. This is exactly the kind of signal researchers watch closely, without treating it as a single proven cause. Weather patterns rarely trace back to one clean explanation, and this one involves several factors layering on top of each other at once. Now, for the genuinely speculative angle, and I want to be upfront that this remains an active area of ongoing research rather than settled science, some climate scientists have proposed that Arctic warming, which is happening faster than warming at lower latitudes, may be weakening the temperature difference that normally keeps the jet stream moving briskly. The theory goes that a smaller temperature gradient between the Arctic and the mid-latitudes could make the jet stream more prone to these slow, wavy, stuck patterns. That idea remains genuinely debated within the climate science community, and not every researcher agrees on how strong that link actually is. I'm including it here because it's a useful context for understanding why patterns like this split jet stream might become more common, not because it's a proven mechanism behind the specific event. Good science reporting means being honest about where the evidence is still developing. Let's also be clear about what forecasters cannot do, even with all this data in hand. Nobody can tell you today exactly how long the western heat dome will hold, or precisely where the jet stream sets up next month. Long-range pattern forecasting can identify likely tendencies weeks out, but it cannot deliver day-by-day certainty that far in advance. That's simply a limit of current atmospheric science, not a failure of the meteorologists tracking it. What forecasters can tell you is what typically comes next in a pattern like this one. AccuWeather's long-range team expects the North American monsoon to become active by the middle of July, which would begin shifting winds from the west to the south. That shift usually brings more humid air flowing northward into the west, eventually increasing thunderstorm activity there. Early. In that transition, though, the risk of dry lightning and wildfire ignition tends to spike before rainfall becomes reliable enough to offer real relief. I cover pattern shifts exactly like this one almost every day, because these are the setups where understanding the mechanism actually helps you plan better than just watching the daily forecast number. So here's what this means practically, depending on where you live right now. If you're in the western US under this newly built heat dome, prioritize hydration and avoid outdoor exertion during peak afternoon hours, typically between 1 and 6 p.m. Check on elderly neighbors or relatives specifically, since heat-related deaths disproportionately affect older adults and people without reliable air conditioning. A quick phone call or visit during a multi-day heat event can genuinely make the difference. By early July, this heat wave had already been linked to 44 deaths, a reminder that these patterns carry real consequences well beyond broken temperature records. That number is exactly why understanding the mechanism behind the pattern matters, not just tracking the daily high. If you're in a wildfire-prone area of the interior west, pay close attention to red flag warnings over the coming weeks as the monsoon transition begins. The early dry lightning phase before consistent rain arrives is historically one of the more dangerous windows for fire ignition. Keep an eye on local air quality reports too, since temperature inversions under a heat dome can trap wildfire smoke close to the ground. That combination of heat and poor air quality is especially hard on anyone with respiratory conditions. It's also worth having an indoor backup plan ready if your area loses power during this kind of extended heat event. Know which nearby public buildings, libraries, or designated cooling centers stay open, since AC failure during a multi-day heat dome is when heat-related emergencies spike the fastest. For pets and outdoor animals, move water bowls into shade and check them more than once a day, since standing water can heat up surprisingly fast under direct sun. Pavement temperatures can also climb far higher than air temperature, so early morning or late evening walks are safer than midday ones. If you're in the east, don't assume you're fully in the clear just because the ridge has shifted west. These patterns have swung back before, and the same wavy jet stream that sent the block westward can just as easily send another one east later in the season. Keep basic heat supplies on hand even after the immediate wave passes, including extra water, a portable fan, and a plan for cooling one room of your home if the power grid gets strained again. Grid stress tends to follow these patterns closely, since air conditioning demand spikes exactly when the system is least able to absorb it. Sign up for heat alerts through your local National Weather Service office if you haven't already, since those notifications tend to arrive faster and with more specific local detail than general news coverage. That's especially useful once the pattern starts shifting again. The bigger takeaway from this entire investigation isn't really about any single number, whether that's 111 degrees in Billings or 106 in Atlantic City. It's about understanding that a wavy, stuck jet stream can move a single dangerous pattern across the entire country like a spotlight sliding from one region to the next. Once you understand that mechanism, the headlines about back-to-back record-breaking heat waves in totally different regions stop looking like a coincidence. They start looking like exactly what they are: two acts of the very same atmospheric story. If breakdowns like this help this kind of weather pattern actually make sense, hitting subscribe means you won't miss the next one. I'll be back the moment this pattern shifts again, with the updated numbers and what they actually mean for wherever you live.